Okay, so chapter 10 deals with elasticity and simple harmonic motion. Basically, we've been dealing with what is in a circle. Oopsie, I hit that. And instead of just staying in a circle, we're now going to more or less graph it. And when you do graph it, notice that this little red dot stays the same. Um, well, stays the same with respect to the y-axis, but it bounces up and down. So if you take that little ball and you were to graph it, you get what we call a sinusoidal graph. And so that's generally what's called simple harmonic motion, as it creates that little pretty sine or cosine, in this case sine graph. So this is where all your trig comes to play. So, yay. All right. But I start off. I don't know if your book starts with this, but I always start with it. We're going to start off with stress versus strain, or stress and strain. Um, in engineering, stress is the deforming force per unit area. And so that, let me find my cursor. There it is. So you're looking at force per unit area, newtons per meter squared. This actually, and I don't know how much we talk about it, this is a Pascal. It's defined to be a Pascal. You can actually express it either way. But Pascal is the true unit, and that's a newtons per meter squared, so force per unit area. There are different types of stress, and I'll go into detail of each one here in a moment on separate slides, but there is tensile stress, shearing stress, and then there's hydraulic stress. So stresses are essentially pressures. You can think of it that way. Then there's something called strain, and strain is the unit deformation. Basically, when you have a stress or a pressure applied to something, it's going to deform. If I have a balloon and I apply a stress by just squeezing it, it's going to deform. That deformation is called strain. Stress and strain are both proportional, which makes sense. You know, the more stress you have on something, the more strain. The more pressure you put on something, the more it should deform. So the more stress you have, the more strain. And there is a proportionality constant, and it's called the modulus of elasticity. And so stress, and I'll go over this a little bit more detail here in a couple slides here, but stress is the modulus times the strain. And I'll give you a formula for that, well, I guess 2 slides from now. But first, we have to talk about a stress versus strain curve. Um, the stress versus strain relationship is linear until it reaches a certain point that I called based off of this, because your book doesn't delve into this too much, but I feel like it's important. SY, which is the yield strength. And after this point, the object will no longer retain its original shape when the stress is removed. So think of it as a fork. If I bend that fork to a certain point, I could bend it so that it's, I don't know, looks really funny, and, you know, it's almost practically in a circle. That would be past the yield strength, because if I let go, it's not going to go back to its original shape. And that's demonstrated by right here. Oopsie, that's not good. There we go. Where you're linear, this is the, as you apply more and more stress, nothing happens to your fork, nothing happens to your fork, and then all of a sudden you hit the yield strength. At the yield strength, that's when your fork doesn't go back to its original shape. And then you can keep applying pressure. You keep applying pressure, and eventually it will rupture. And this little area right here after the yield strength, over here, this is the range of permanent deformation. So we're not going to have, well, you're going to have deformation definitely while you're getting to the yield strength. Your permanent deformation will occur after you go to the yield strength, but before you hit the ultimate strength. And then that's kind of where I talked about how it hits the ultimate strength. And so this is a, you know, nice little stress versus strain curve. And I showed this last time I taught a class, but there's a King of the Hill episode where they build a McMansion next door to Hank Hill's house, and of course it collapses during a freak storm. Mark Derico. And it's interesting because the creator of King of the Hill actually has a degree in physics, and so it actually talks a little bit about it, and it's a really short clip, so I'll show it. But I don't know, it's kind of funny.
Sledgehammer marks. It was the act of rednecks on a drunken rampage.
We don't have anything to hide. The only one who did something wrong here was you. Your shoddy McMansion was going to destroy our homes. We only took it down in self-defense. And for the record, nobody was drunk.
There's a chance I may not have been within the legal limits.
I'll see you in court, or more likely in the office of a retired judge, as these issues tend to go to arbitration.
This next exhibit, Exhibit 42, will demonstrate the inferior tensile strength of Mr. Wasanasong's fiberboard to that of construction-grade plywood. Here, go ahead and pass these around. Now, for those unfamiliar with tensile strength ratings, I've put together a stress versus strain graph.
Mr. Hill, when is this trip to the hardware store going to end?
Hank is stinking up the place with all his boring facts and figures. People want damning evidence and courtroom drama. He needs to throw a briefcase like Mr. Brady. Something.
Now is the...
Anyhow, so this is kind of a stress versus strain example that you could actually see in a TV show, albeit a cartoon, but everything that he said is pretty legitimate, because like I said, he has a degree in physics, so it's kind of funny. But anyways, yeah, so stress versus strain, this is kind of an example that shows you that it actually is used a lot in engineering and construction and things like that. Now, I told you I'd go over each one in detail, so we'll start off with tension and compression. And that's basically tension or tensile stress is if you have, let's say here, a rod. That is a really bad rod, but I know what I can do to make it a good rod. I learned this little fancy trick. If I could find my cursor. Yeah, look at that. Oh, what a good rod. And I made a mark. There we are. So basically, it's you could push or pull, let's say, a rod in the direction of the length. That is tensile stress. And so you have the formula is force over area, otherwise known as pressure, is equal to E. This is called your modulus. This E value, and you can get a bunch of these in the book, and I'll give them to you like for these problems. But this is called the Young's modulus, and we'll do a problem here doing it. And then it's the delta L over L. This is your deformation. Deformation is unitless because it's the change in length of your original length. And then if I go back up where I told you this earlier, it's the modulus times your strain. And remember, your strain is your deformation. And so here's your modulus, your E. I lost my cursor again. Times your deformation, delta L over L. And all of the equations for tensile, shear, and compression, or sorry, tensile, shear, and not quite compression, but hydraulic. I'm blanking on that for some strange reason. All of them have a very similar setup for their equation. F is force, A is area, and I already spent delta L over L. But yeah. Shearing. Shearing is a little bit more complicated. So let me show you what shearing is. There are two examples. A popular example is, let's say you have some Jell-O, and you apply a force on the Jell-O to the right. Well, the original shape of the Jell-O is going to be something like this, right? And when you push it, it's going to be compressed by a distance that we will call delta x. So the compressional distance goes up and down, whereas the force goes left and right. So that's a key part of shear, is that the force is going to be perpendicular, more or less, to the length, depending on the setup. Another example is, like, let's say you want to break a stick. Oh, this is Jello. Yeah. If you press your force against that stick, that's going to be shear, because your force is then also perpendicular to your length. And so that's the key part of shearing. The setup is the same, except that we have G, which is your shear modulus. And as I said, delta X is the deformation that's perpendicular to your length. Other than that, it's the exact same equation. Hydraulic is the absolute easiest one to understand, because it's basically force from the fluid. So basically, if I'm inside the water, there are forces all around me from the fluid. So that's hydraulic stress. Generally, strangely enough, they just represent it by a P for pressure. It's still force divided by area, by the way, but a lot of books just use a P for pressure. B is your bulk modulus, and since we're dealing with a volumetric change from all sides, is delta V over V. And so those are your three different types of stresses. So we'll do an example problem. We have an 80 centimeter long, 1 millimeter diameter steel guitar string, and it must be tightened to a tension of 2,000 newtons by turning the screws. By how much is the string stretched? So this will be a tension problem, because it tells me tension, so it's tensile. So I'm going to use the first equation that we went over. So that'll be F over A is equal to Y delta L over L. We want to know delta L, how much it's stretched. So I'm going to multiply both sides by L. That gives me FL, or Florida, over, looks like AY. And that's not a state. And that's equal to delta L. And so I just plug in what I know. Okay, well, the force is 2,000 newtons. The length is 80 centimeters, so I'm going to put 0.8 meters, because that's centimeters, and we need meters. Divided by A, which is area. Oh, got it. Pi, and I gave you the diameter, so I need the radius. So 1 millimeter, half of that's going to be half a millimeter, so that'd be 0.0005. And I forgot my units. And then the modulus. Oops. So 8.1 e to the 10th newtons per meter squared. All right, calculating time. Did I say y or e? E. Sorry. E. I said y for the modulus, but that was supposed to be an e. Your book uses e. Sorry. It's the same thing, but some books use different letters, and I get confused sometimes. All right, so 2,000 times 0.8, divide that by my friend pi, divide that by 0.0005 squared, and then divide that by 8 times 0.1 times 10 to the 10th, so E10, and that gives me 0.025. So that's 0.025 meters, or it's going to change length by 2.5 centimeters. So that's kind of the handy part of these equations, is if you know the amount of force you're applying, you can actually figure out how much an object will be elongated. And if you have the stress versus strain curve, you can also tell at what point you'll have permanent deformation. Because if you're, you know, uh, tightening a guitar string, you can actually tighten it too tight, or you can tighten it to the point where it ruptures and you reach the ultimate strength. And so that's kind of the handy part of some of these equations. Okay. Ideal and simple harmonic motion. Ideal springs, sorry. The force required to stress or compress a spring can be described by Hooke's law, which is F is equal to negative kx. So your book, I believe, uses a positive kx. So most of the time, can't find my cursor. There we are. You could just use kx. But the true nature of the equation is to have a negative. And the reason that it's negative is that its displacement and the force are in opposite directions. What do I mean by that? Well, I have a picture over here, a couple slides from here. This is a spring that's allowed to go back and forth. And in this case right here, the spring is stretched out too far. So the spring force is pulling it back to the left, but the displacement from equilibrium, x, is actually to the right. Whereas if I go all the way at the bottom where the spring is compressed to the point where it's ready to kick out this way, the force is pushing it this way, but it's actually not at equilibrium, because here's the equilibrium right here. It's actually to the left of that. So your spring force and your displacement are always opposite to each other. You can pretty much get away with all problems of just saying F is equal to kx. But the true nature, it should be a negative. So that makes a little bit of sense there. K is your spring constant. And your spring constant is measured in newtons per meter. And X is the compression or the decompression of the spring. Excuse me. You can see that it's similar to the setup of the tensile and shear and some of the other forces there. Whereas F over A, your pressure is equal to E, your Young's modulus, delta L over L. Any of those, it's a very similar setup. So that's kind of interesting. Thought there was one more thing I was going to say, but I can't remember. So I'll go ahead and do a problem. All right. Let's say a 100-kilogram man, so 222 pounds roughly, stands on a trampoline. It depresses a distance of 23 centimeters. What is the spring constant of that trampoline? So we use the fact, and I'll just use the positive version, F is equal to kx. We're looking for K. The force is going to be the weight of the man. So this is going to be mg is equal to kx, and we're looking for x. So it's just going to be mg over k. There we are. So I take his mass, 100 kilograms, times 9.8. And then I divide that by 0.23, because a lot of times your values for the compressional distance isn't going to be too high. So a kilogram meters per second squared, that's a newton, and meters is on the bottom, so that's where we get our newtons per meter. So 100 times 9.8 is 980, I already knew that, divided by 0.23, and I get 4261. Can't find it. There we go. What that means is that it takes 4,261 newtons of force in order to depress the trampoline 1 meter, assuming it doesn't hit, say, the yield or the ultimate strength. So most of your compressional distances for larger things that we deal with are going to be small, and your spring constants are going to be high. Another thing to note is it's not always F equals kx out there in the real world. Sometimes it's kx squared, sometimes it's kx cubed. It really kind of depends on the materials, and it's going to be on the scope of this class, but we just go with F equals kx for this physics course. Alright, so there's a conceptual example 5, and let me draw a picture here, and I have something else that I'm going to do. Basically, let's say we have a spring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have a mass attached to said spring. Okay, so there are 10 springs. Coils, sorry. And then, okay, well, what if we cut in half? What happens? Well, we'll have obviously half the number of coils. So it'll be 1, 2, 3, 4, 5, not drawn to scale. Okay, and so we'll have 5 coils. But here's the interesting thing about that. Whether we cut it in half or not, the displacement from equilibrium, x, well, I know it's going up and down, but we're going to call it x for this case, is actually the same, whether we have the 5 coil spring or the 10 coil spring, because after all, well, it's still made of the same material. So the displacement is the same. So mathematically, kind of looking at it, we know that F is equal to kx. Okay, and then let's say let x equal delta x, which will be the change in length per spring. Coil. So it'll end up being delta x over 10 because we have 10 coils, right? And so this is then going to be F is equal to K delta x over 10. Okay, but if we cut in half, we'll have half the amount of coils, right? Okay, so that gives me F is equal to K delta x over 5. The problem is that we know that delta x over 10 was equal to x, the actual displacement. And we know the displacement is the same in both setups. So the only way this is going to be the same is if I multiply the top and the bottom by 2, because the force applied is the same. And that 2 will pull out here, and that becomes 2k delta x over 10. So now we have the same exact setup, except the fact that there is a 2 in front of the spring constant. That, interestingly enough, has implication, and that the spring constant of the shorter spring is twice that of the original. That means shorter springs are stiffer, which is extremely counterintuitive. But the math works out, and I don't have a demonstration for this, but I do have something I found in PHET, the physics, that they have a bunch of physics applets and things like that. These are the same springs. The only difference is one of the springs has 5 coils, the other one has 10 coils. There is a blue line right here. That's the natural length of the spring, and you can tell when it comes back up, it's the, well, indeed, natural length before it got pulled down. The green is the equilibrium position. That's just the resting position before it starts going into a complete oscillation. But notice that between the natural length and the equilibrium position, this is 15 centimeters. And also 25 centimeters to 40, that's also 15. So indeed, the lengths that the springs are going to elongate are the same. So that's why shorter springs happen to be stiffer springs. And you can also tell here that the coils are elongating much more, almost twice the distance, and they should, because it's, you know, half of the number of coils, that the bigger spring has as well. So that's kind of a key to remember, and this will probably show up on your test, so don't forget it, but that shorter springs are indeed stiffer. All right, and so I talked a little bit about this, but when the restoring force of simple harmonic motion is negative kx, then the motion is said to be simply harmonic. Basically, a simple harmonic motion means it's going to oscillate forever. So the best example I have is what I just showed you. I could speed these up a little bit. But simple harmonic motion just means it's going to oscillate back and forth, pretty much forever. Most things don't oscillate back and forth forever. Friction slows it down, but there are applications out there that are practically going to go on forever, and for a very long period of time at least. And so you can approximate it as simply harmonic motion. All right, so this one, this is kind of misleading. Basically, this is a proof that I'm going to do, or a couple of proofs. But first, let's start off. What is actually an amplitude? That's the excursion from equilibrium. So in the earlier example, where the going really far back to the beginning of the chapter, where they had the ball going back and forth along the line and created the sinusoidal graph. The amplitude is the displacement from equilibrium, whereas the equilibrium here is the y-axis. So this would be your amplitude. Another example, and I still have it up, is the springs. The red line right there is the displacement from equilibrium, and you know that's equilibrium because it's green. And so that little distance right there is the distance, maximum distance from equilibrium. Given that, we now have to kind of come up with a very basic wave equation, which I will show you. Let's have a ball going back and forth, more or less along a circular axis, like we did at the beginning of the chapter. So if I have a circle, and let's say I have little particles at this point right here, it has a tangential velocity. Let's make this straight because we can. Going off right here. This would be your tangential velocity. Now that tangential velocity is going to have components to it, just like every other thing has. This is a little, let's get rid of that. There we are. It'll have a horizontal velocity component, Vx, which will go to the right, and a vertical component, Vy, which is going to go up. Because, well, it's going to have components. So everything has x and y components. Whether or not they're 0 or not is irrelevant. Then, they're referencing the center of this circle. The radius is going to be, we're going to have a line that's going to extend out to our little point right there. And then we will also create an x-axis and a y-axis. So we have a nice little setup right here. Now, this angle right here, this inner angle theta, by similar triangles is, and I probably should have drawn this bigger, hindsight, is congruent to this inner angle right up there. Because it's just this triangle, which I'll make right here, just literally flipped around. The reason that we're doing this is because we want to create an equation that's going to describe basically a linear velocity equation that will describe the motion of said object. So let's find out, well, let's look at Vx. Vx was the horizontal component. It's kind of hard to see because I didn't make this big enough, but that's along this line right here. And Vx is going to be the sine because it's far away from this angle right here, instead of a cosine, which we normally deal with. And so Vx is going to be a Vt times the sine of theta. So what I'm doing right here is I'm taking my tangential velocity and I'm finding the component that goes left and right, because remember we had that little ball and the ball went back and forth left and right. So we need to at least we want to describe that motion. So we know that Vx is equal to Vt sine theta. Vx is going to the left, so I'm going to make this a negative Vt sine theta. Now, the radius happens to be your amplitude. because the ball is going to go back and forth along this axis where this is equilibrium and this is equilibrium. So amplitude, amplitude. We call amplitude A. So A for amplitude. And remember that from last chapter, Vt was equal to R omega. Well, we already know our radius is the amplitude, so A. So Vt is going to be A omega. So looking at Vx, that's going to give me a negative A omega times the sine of theta. So now we can use our angular frequency. We can use the amplitude and the sine of an angle to find the horizontal velocity at any given point as the ball moves back and forth. Sometimes you want to find a maximum velocity. And when you want to find your maximum velocity at the maximum, sine of theta would need to be equal to 1. And so obviously you're thinking 90 degrees, which would be fine. And so the Vmax is going to be A omega, well, times 1, or simply A omega. For conventions, the sign is generally dropped because I know that was a negative A omega up there. But the maximum velocity equation, they generally are going to keep it as positive. At least that's the equation that they give them, even though we started off as negative and proving it. And like I said, it occurs at 90 degrees, which would make sense because that would mean it's moving fastest at the top right here. So physically made a little bit of sense. Likewise, we could come up with, I think I have enough room here. I do, yay. We could come up with equations for acceleration using the same type of situation. So let me, I could draw it right here. I can fit it, right? Sure. Where we have a point at the center. Let's put it, that same point we're going to use. We know that that point will have a centripetal acceleration pointing towards the center. And we want to find, let's say, AX. Oh, I need to rewrite that. Let's just erase that. That'll be fine, right? Yeah, sure, it'll be fine. AX. So we want to find that component right there. Going back to my previous example and drawing pretty little lines. Oh, it's not good. Let's try this again. I can do this. Nope, that's not good either. Try this one more time. Nope, that's not going to work. There, that looks good. Now drawing a beautiful XY axis. Perfect, got it. We know from our previous picture that this inner angle theta, well, this is just alternate interior angles. So if we want to find AX, we want to find the cosine of this angle theta. And so AX is then going to be AC, our hypotenuse, and then cosine of theta. AX is going to the left, so I left some room here so that I could put in my negative. Obviously not enough room, but it was my intention at least. All right, well, if you recall from the previous chapter, AC was R omega squared, and our R is our amplitude in this case, so A omega squared. And so I get AX is equal to negative R omega squared cosine of theta. And just like the previous problem, we also have a maximum acceleration, and that's going to occur at A omega squared. Because a lot of times the book will ask you for questions about the maximum velocity and maximum accelerations. So, just a thought I had in my head and I already forgot. Oh, yeah. So if you've had calculus before, obviously it's not required. You may notice that if you take the derivative of the Vx right here, this little function right here, you end up getting the acceleration. So it physically, or rather calculatiously makes sense. If you don't have calculus, you don't need to listen to what I'm saying. You can just ignore that part. Okay. Um, so, some couple other new things here. We know from chapter 5 that 2 pi r over t was the velocity, and we know that omega is 2 pi over t. Frequency is commonly used, measured in hertz, and that's 1 over the period. Therefore, and I can't remember, I feel like I have talked about hertz. I do this every year. I can't remember if I have or not. But hertz is a 1 per second, and we call that, sorry, frequency is a 1 per second, and we call that hertz. So we want to sometimes express angular frequency as omega is equal to 2 pi f. And that will, it's better to use angular frequency because regular frequency generally deals with like oscillations, whereas angular frequency can kind of do what's in the middle because it's measured in radians per second. And so that's what we're going to use from kind of here on out. Angular frequency of a certain wave is 5 radians per second, so that's my omega, and the maximum speed is 10 meters a second. We need to find the amplitude and the max acceleration. So, all right, so we know that our omega is 5 rads per second, and we also know that V max is equal to 10 meters a second, and we want to find amplitude. Well, from earlier, I told you that the V max is equal to A omega, and we know that this is 10. We don't know A, but we're looking for it, and we do know that this is going to be 5 radians per second. So, your seconds cancels, radians isn't a true unit, and we get an amplitude of 2 meters, so that makes sense. Then it wants max acceleration, and from the very 2 slides ago, we know that that's A omega squared, which we can now find that we have amplitude. So I will take my amplitude of 2 meters, and I will plug in my 5 radians per second, and we square that crap, so that's 25 times 2, and that'll be 50 meters a second squared. So basically, if we have an object going back and forth, we can use some of this information to get its maximum acceleration. So let's say you have some sort of oscillator and it can only withstand a certain amount of G's. This way you can actually calculate, well, how many G's, well, I don't know what G force is, but G's is that actually going to go through. And so you can use the maximum acceleration equation to get that. So it's got some handy things out there. Okay, frequency of vibration. So now we want to relate, let's say, angular frequency to, say, a spring constant. We know 2 things at this point. We know that F is equal to negative kx. And we also know that F is still equal to ma. So we know our force is equal to mass times acceleration over the spring constant times the displacement. Therefore, we can say the mass times acceleration is equal to kx, or negative kx in this case. If we plug in acceleration, and if we plug in the equation of motion, at least for position, and let me show you this. I didn't quite go over this in the previous slides because it's not used as much, but this is the equation of motion. We did do this one, and this is the equation of acceleration. But if you plug both of those in, your cosine omega t's would end up canceling, and you would get something really nasty, but let me show you. This gives you m negative a omega squared cosine of omega t equals negative k a cosine of omega t. That doesn't look like a cosine omega t, but that doesn't matter because all that crap is going away. Negatives become positive peats. That gives me ma omega squared is equal to ka. A's now go away, and then we get the omega is equal to the square root of km. So the angular frequency of your simple harmonic oscillator is going to be simply the spring constant divided by the mass rooted. Well, square rooted to be exact, because rooted to the second. But you get what I'm saying. So we can use that equation then to get the angular frequency, and we will do that, I believe, on the next problem. Oh, yes. A particular bed has a spring constant around 8,000 newtons per meter. Actually, beds have like their own math dealing with springs and things like that. And then there's posturepedics and all sorts of other things that kind of change that scene. But yeah, any case, 8,000 newtons per meter was the angular frequency of a 35 kilogram child bouncing on the bed. This one's really simple. Probably should have picked a more difficult one, but all you got to do is omega is equal to k over m square rooted. We're just looking for omega, so I just simply take my spring constant of 8,000 newton, try this one more time, 8,000 newtons per meter divided by 35 kilograms. And I didn't put a square root for some reason, so we're just going to raise it to 1/2 power and call it good. How about that? That's what I do in my calculator anyways. I don't even know what the square root button is. So I just raise everything to the 1/2 power, if you haven't noticed already, as I talk this through. 15.1 radians per second. Sometimes you actually see this written instead as m omega squared is equal to k. If you take any upper division mechanics courses, you'll see that often. It's sometimes easier to express the spring constant in terms of the mass and the angular frequency for certain applications. Okay, like everything else, a spring has energy. We have gravitational energy, kinetic energy, etc., etc. There is a spring energy. And that is in a familiar form of 1/2 kx squared. Just like 1/2 mv squared for translational kinetic energy, 1/2 I omega squared for rotational kinetic energy. And then there is also 1/2 now kx squared for spring potential energy, or rather the work done by a spring. And so how do we come across that? Well, I will show you. Let's say I have a little spring, and that's not there because I lost my cursor again. Not sure why I always lose my cursor. And let's say that my... Alright, let me draw this out a little bit better here. And let's say that we'll have an initial position and a final position. I'll say it's like going that way for what we're doing. And I didn't really draw a good arrow. So let me try that again. There we are. Let's say we want to find the average force. Well, we know that force is equal to negative kx. We'll just be positive in this case. So we'll say the displacement's to the left anyway, so we can get rid of the negative. And we know that. But let's say we wanted to find the average force. Well, that would be kx. I'm going to put naught first, since it's the original. Kx naught plus kxf divided by 2 is going to be your average force. Now, why do I want to get that? Because I want to get the work done. And I know that the work, as soon as I can find my cursor, is going to be a force times some sort of displacement. And my displacement is going to be x naught minus xf. Or I could say xf minus x naught and make this negative up here. In either case, the negatives cancel. Not sure why I chose this way, but it works all the same. In any case, so my work, find my cursor, here it is going to be force x naught minus xf. And then my force is 1/2, pull that out front, kx naught plus kxf times x naught minus xf. And then you multiply that through, cursor, 1/2 of kx naught squared minus 1/2 kxf squared. We usually just take 1 point of that, and so we simply just call it kx squared. And that will give you the work done by the spring or even the potential energy of said spring. It goes either way when you're looking at a spring. So I usually just express it as the elastic potential energy of a spring, and I say that that's 1/2 kx squared. 1 way to skin a cat, but that's kind of how I usually. Alright, so this is a bit of a classic problem. Basically, you have an object that rolls down a ramp and hits a spring, and the spring compresses. In this case, we use a Swedish meatball. One little disclaimer is we're assuming that it's not rolling because I didn't give you the rotational inertia of it. So, one little disclaimer, not rolling. Meatballs probably wouldn't really roll. It would probably kind of slide, maybe roll a little bit, but we'll assume there's not a lot of rotational motion there. The reason I say that is because, well, let me read the problem first. 40 grams Swedish meatball thrown down a frictionless ramp, because Swedish meatballs. 5 meters a second is shown from a 1.9 meter ramp. We want to figure out how much the spring compresses if the spring constant is 500 newtons per meter. So we have to use the conservation of energy, but we have to kind of look at it a little bit differently than we have been. We still look at, do we have initial kinetic, do we have initial potential, but we also have a spring potential that we have to deal with. Now, I could find the speed at this point right here and then do the conservation of energy again to see how much is compressed. But the beauty of the conservation of energy is I can literally just take the starting and ending points. And so that's what we're going to do. And so we'll have a final kinetic, final gravitational potential, and then a spring potential. So over here, we do have an initial kinetic, so that stays. And we do have an initial potential energy, so that stays. We don't have the spring because the object is not acting on the spring, so there's no spring potential. On the other side, we do not have a final kinetic energy because once the spring is compressed, the Swedish meatball will stop. And also, it has nowhere to go gravitationally, but we definitely will have some spring potential because what it's going to do is that spring's going to compress and push it right back up the ramp. So, using our conservation of energy, it is K naught plus PE naught equals KF plus PEF, assuming both types of potential energy. We do have, remember, we don't have final kinetic, but we do have initial potential, gravitational, and kinetic energy. So that's going to give me 1/2 mv squared plus mgh equals 1/2 kx squared. Mass isn't canceled now because now we're dealing with a spring, which mass isn't part of, and even if it was, I'd have to have the mass of some other necessarily object, or at least have the angular frequency to work with it. So I need to solve that for x squared, so I can multiply both sides by 2, divide by k, and take the square root. And that's going to give me mv squared plus, I forgot my 2, plus 2 mgh all over k square rooted is equal to x. So I'm going to pull out my mass inside the square root, so I'll have to write slightly less. So that's going to be 0.04 kilograms. And then inside my box is going to be my velocity of 5. That was my initial velocity. Plus 2 times 9.8. Extend this a bit. And then times 1.9 for the height. And that's all over the spring constant of 500 newtons per meter. Closing brackets. Okay, so let's do that. Let's do it within parentheses first. So 5 squared plus 2 times 9.8 times 1.9. Okay, multiply that by 0.04. Then divide that by 500. And then I'm going to take the square root of that, and I get 0.07. Now, this is in meters. So if we express that in centimeters, we get 7 centimeters. A pretty reasonable value, assuming that, we know that Swedish meatballs roll down ramps. But anywho, kind of a fun problem where you combine use the conservation of energy, but throw in now spring potential, or the work done by a spring. Either way, either direction we want to go with that. A related problem, trying to find something very similar to that. This is the KVLY TV tower. It's in North America, particularly it's in North Dakota. It's actually the tallest structure in the all of North America, way taller than Sears Tower, or Willis Tower, I'm sorry. That's what it's called now. It's actually 2,063 feet, quite tall. So it's 628.8 meters. And we're assuming that a Raider, 90-kilogram Raider, falls off of that tower and it falls all the way to the ground. We're assuming there's little atmosphere in the future. They're wearing like a gas mask because it helped my numbers out. And that the soft ground, let's say, has a spring compression of around 1 times 10 to the 6 newtons per centimeter. So this is a little bit different. It's per centimeter, so we got to be careful with that. How much will the ground depress upon impact? So kind of the same deal here. We look at the top where he's falling, so no initial kinetic, but we will have initial gravitational potential. And when he hits the ground, remember, he's going to hit the ground and it's going to sink. And at that point, we're trying to find that displacement. So at that final point, we know that they're going to have a spring potential, and we know we're not going to have kinetic. So in this case, we have kinetic on neither ends, which is kind of fun. So I take remember that is K naught plus PE naught equals KF plus PEF. And so we have no kinetic on both ends. So basically, I like to do this problem, even though it's kind of a repeat of the other one. It just shows you that all the initial gravitational potential energy goes into the energy inside the spring, and then when it springs back out, it goes right back into potential energy, assuming no loss of energy, which is literally how conservation of energy works. Okay, well, this is mgh, and this is 1/2 kx squared, so that'll be 2 mgh over k rootified equals x, and so let's do that. 2 times 90 times 9.8 times, really high value, 628.8, and then I have to divide that by k, and I didn't put my numbers in here, I just realized, so let's write down my numbers. I just jumped right ahead. That'll be 2 times 90 times 9.8 times 628.8. And then I got to be careful because everything's in meters, but it gave me the spring constant in newtons per centimeter. And so since it's in newtons per centimeter and I want to get it into meters, I know that there are 100 centimeters in a meter. So what I'm going to do is multiply that value by 100. Or move the decimal place twice, so that's going to be 1 times 10 to the 8th newtons per meter. Okay, now I'm going to divide that by 1e8, and I'm going to raise that to the half power, take the square root, and I get 0.1, so around 1 centimeters. So, fun little problem. Alright, I believe this is our last topic, and it is a pendulum. So, fun. Alright, how do I want to do this? We'll go that way. Alright, let's draw a picture of a pendulum. Let's work from there. All right, so let's say here's my little axis, and here I have a little pendulum, and let's say it has length L, and this is its original length, and it goes through an arc we'll call S with angle theta, and it has an amplitude that we will call A. Okay, so, oh, the bob. The bob has weight. Bob has weight? Yes. Bob is my father. Bob has weight. Um, it has weight, and it's pointing directly down. All right, so we're going to try to come up with an equation of motion for a pendulum. I know I could find torque, and the torque is going to be remember, it's a force times your lever arm, or the force in this case is going to be mg, and its lever arm is perpendicular to it, which is going to be your amplitude, and it's moving to the left, or you can even think of it in clockwise position, because we're assuming it's going to be restored this way. So we make that negative. Amplitude is nothing more than L sine theta, so I can say negative mg L sine theta. And then I happen to know that at, don't even vary, just small angles, that sine theta is approximately equal to theta. So I can now say tau is equal to negative mgl theta. Okay, well, this is very similar to the torsional pendulum where it rotates back and forth, but this is extremely similar to our F equals negative kx, the original Hooke's law that we started with, albeit it's moving with respect to rotational terms. And given that they're so similar, we can use some of the approximations. Like, for example, we need to find my cursor here. We know that earlier I showed you that omega is equal to the square root of k over m. And so you can think of it as this being your k right here. And so I can say, okay, well, that's the square root of mgl. And since we're rotating, this one was linear, the f equals negative k, so this one's rotational. And so your m becomes an I, or rotational inertia. This isn't really a true proof. Honestly, I think the proof involves some partial differential equations to actually do prove this, but it's just kind of a thought experiment to get to the equation. So omega is equal to mgl over I. This is for something generally called a physical pendulum. Pendulum. Oh, it's spelled right there for me. And a physical pendulum would not be as simple as this simple pendulum, which I'll get to in a second. A physical pendulum would be like a bowling ball rotating along some point right here. So, a couple things I need to kind of also talk about. Remember, omega is equal to 2 pi f, or 2 pi over t. I will come back to that in a second. And one other thing is, I mentioned that this is a simple pendulum. Well, for a simple pendulum, we assume that the bob is really small relative to the length, and we just assume it's a point particle. And so for a point particle, if you recall, the rotational inertia is just going to be equal to mr squared. R is your radius, and in this case, your radius is just going to be L. So, factoring that's going to give me omega is equal to the square root of mgl over ml squared. L cancels, one of your L's, m cancels, one of your L's cancels, and that gives me omega is equal to the square root of gl. This is the angular frequency for a simple pendulum. We don't normally use angular frequency when we deal with pendulums. So I also know, coincidentally, from up here, that this is also equal to 2 pi over t. And so what I can do is move t to one side and move the g and the l to the other. And that's going to give me t is equal to 2 pi square root of L over G. And this is your general equation for a simple pendulum that we're generally going to use. I listen to the word generally a lot. There's a lot of different things you can do with this, but you could probably get away with just using this equation. And that all just comes from just basically a picture and figuring out the torque and seeing what it's like and comparing it to something else and then kind of extrapolating from there. So I'll do a problem. It's rather a simple problem, but I always point something out here. We want to figure out the length of the pendulum if the period is 5 seconds. T is equal to 2 pi square root of L over G. I always have to think of that one because I reverse the 2 sometimes, but meters cancel, seconds flip up to the top. So if I want to figure out the length of the pendulum, I could square both sides, and that's going to give me t squared is equal to 4 pi squared L over G, or gt squared over 4 pi squared equals L. So, plugging in numbers, this is 9.8 for G. The period is 5 seconds squared. And then divided by 4 pi squared. Okay, so I take 9.8 and I times that by 5 squared, not 5 log. And then I divide that by 4. Now, whenever you divide by pi, at least if I recall it still does it. I have not tested it in a while. I should maybe test it at some point. Some calculators, I believe it's a TI-83. If you divide by 4 pi squared, it like divide by 4 and multiply by pi squared. So be careful to put the pi's in parentheses. It never hurts to parentheses the crap out of everything. That way your calculator knows the correct order of operations. In any case, you get a very massive pendulum of 6.2 meters. That's like 40 feet. That's one of the bigger pendulums you might find in museums. Pendulums are interesting because, as you note, that there's a g in there, and if you know the period of a pendulum, you can work backwards to get the acceleration of gravity, and you can get it pretty accurate with a pendulum. Definitely down to the 10th, not quite the 100th, so 9.8, not necessarily 9.80, 9.79, more like around the 9.8, but it's still pretty accurate for something as simple as a pendulum that you could just create by yourself. With an object at the end of a string, so that's kind of fun. Now the last question doesn't really fit anywhere, but one of your homework problems is like it, so I added it this year. Basically, we talked about the graph, and we didn't really do any problems with it, so I'm going to do a problem with this. We're going to use this graph to find the amplitude, the angular frequency, the spring constant, the maximum velocity, and let's say the acceleration at 1 second. So a lot of things. So this graph is a rotational motion of a child on their tire swing. So it's kind of watching the swing go back and forth. An exploration graph from a bored father, part 1. I don't know where I came up with that. It just made sense at the time. Because when I think of having a child, I think it's being pretty boring, to be honest with me. To be honest with you, at least. But in any case, some people say it's really fun, but I always think of someone being really bored and graphing, and at least that's what I would do if I had a kid. And in any case, we need to find our amplitude. So amplitude is displacement from equilibrium. And this is in centimeters. So looking at this, it appears to be 2 centimeters. So that's a really easy one to do. We can easily find that. Angular frequency. That one's going to be a little harder. So normally to measure this, I usually measure period. Peak to peak, trough to trough. So, and we'll have to make an estimation here based off of what I did. So we'll go trough to trough. And this is about, I'm going to estimate, this would be somewhere in the middle. It's going to be 3. We're just going to go ahead and call it 3. This one's a little bit further out, so I'm going to say 7.5. Okay, so the period, coming down here on this one, right? Oh, I can just write out here. It really doesn't matter. No, I need to save that space. Your period is going to be 7.5 minus 3, or around 4.5 seconds. And if you recall, your angular frequency is 2 pi divided by your period. So I can take 2 pi and divide that by 4.5 seconds. So 2 times pi divided by 4.5 is going to give me roughly 1.4 radians per second. So that's how I get that one. Nope, I need to erase that. Okay. All right, so we've got angular frequency. We need to now find our spring constant. And I just noticed one thing. I'm just going to go ahead and throw it in here. I forgot to give a mass on this in my graph. How sad. So let's just assume that our mass is going to be 25 kilograms. All right. So in order to find our spring constant, we know that m omega squared. I'll use a different version than I gave you. How I normally write it. M omega squared is equal to k. Now that we have angular frequency and I just gave you mass, we can actually calculate k. So let's take my m. Where'd my m go? 25 kilograms times the angular frequency, which was 1.4. And so I take 1.4 squared times 25, and that's going to give me 49 newtons per meter. Okay, next up is we need to find the maximum velocity. This one will be a little bit tougher. If you remember, we know that... Oh, actually, this is not hard at all. I was wrong. Vmax is simply just A omega. And we have actually already found amplitude, and we've actually already found omega. This would have been hard if I didn't have it written out like that. And work through it. So yeah, I could just go ahead and find my maximum velocity pretty easily. So let's do that. Okay, so I just take my amplitude, which we said was what, 2 centimeters, so I need to change it to meters. Where'd it go? So 0.02 meters, and then my angular frequency of 1.4. So 1.4 times 0.02. 0.028 meters a second. So max velocity. So 0.028 meters a second. And then finally, we need to find the acceleration at 1 second. This one could be hard. However, I'm just going to scroll back and show you something. Can't remember. This will work right here. Actually, we know that the well, let me go. I think I just wrote it in. No, I just wrote it in. So here's what we'll do. We'll use this. I showed you earlier that acceleration was negative a omega squared cosine of omega t. And so I'm going to use that function to actually get my answer. So negative a omega squared cosine of omega t. All right, we know A, we know omega, and we know t. So we have all the information we need to solve this problem now. So I take my 0.02 meters, and I multiply that by 1.4 radians per second squared, cosine of 1.4 radians per second, and that is times the time of 1 second. So it's really just 1.4. And that'll give you my acceleration. 0.02 times 1.4 times the cosine of 1.4. Oh, one thing. When you're doing this, because I just did it while I was in the process of thinking about it, you do need to change your calculator to radians for this one time. Interestingly enough. So, and I got to make sure I change this back. 0.02 times 1.4 times the cosine of 1.4. And that's equal to a very, very, very small value. But I get an acceleration of negative 4.76 radians per second squared. Or no, meters per second squared, I'm sorry. Okay, now why did I need to change it to radians? Well, notice that right here, it says radians per second. Anytime that you put in omega, and notice that all, well, I wrote them down earlier, but I don't have them up. If you note to self in the future, make sure I put those in there. But I'll just point to these two equations. Note that there's always an omega t there, so anytime you're plugging in omega, something in for omega, that's going to be in radians, which means that you're going to have to change to radians. And then if you're like me, don't forget to change back to degrees, because I generally live in degrees, except for this one small part. All right, so that answers all of these questions about the graph. And like I said, you do have one in your homework. It doesn't quite fit in with everything else that we did, but I went ahead and did an extra problem this year. All right, exam 2. I finished working on it. Maybe make some tweaks to it, but this is about what I'll have. It'll be 75 minutes like the last test. You'll have 22 questions, I think, like the last test. 20 are going to be multiple choice. 9 will be conceptual. So those are the questions where there's not a numeric answer. They're generally not worth as much, but it's either you know it or you don't. I generally at least covered it in the lecture, or it's definitely in the book. So keep that in mind. The others, 11, will be computational. I figured out how to create my own test questions and put them in here this time, because I didn't exactly have the time to figure that out before the first test. So you're going to have 2 numeric response questions, where you're going to have to type in an answer with the units. Of those, I guarantee you one will be a 2-dimensional momentum problem, so make sure you know how to do those, because that is going to be on the test. Some type of 2-dimensional momentum problem. I won't say what the other one is, but if you do the written homework and you understand it, then the other one shouldn't be that bad. But you'll have 2 numeric response questions on this test. I'll probably have more in the 3rd test and maybe more in the 4th test, but I got to try them out first and see how it works, because I've never... That was the first online test I gave. This will be the 2nd one, so I'm going to change some things up and see how it works. All right. If you have any questions, I'm still in room 128 in Jabara from roughly 5 to 6:50, and if not, that is it.